Hello everyone, my name is Pablo Ghiglino. I am the founder of Klepsydra Technologies, and I'm here to present the work we have been doing in Klepsydra in the area of data processing, something we call the ring buffer. We call the presentation There and Back Again as a tribute to the beloved Hobbit book. And the reason for this naming is that what we have developed comes from Earth applications. We deploy it to space, and now we are finding new applications on Earth to this technology, back again. So this is exactly the reason why they call the presentation like this. A short bio about myself. I study electrical and electronic engineering, and I have a PhD in aerospace engineering. I have been working in IT or programming. I've been a developer for more than 30 years, since I was 12 years old. But more importantly, the last 12 years I work a lot in an area called trading system, which I will explain in a minute. And for the last 3 years, I have founded my own company, Klepsydra Technologies, where I am working on at the moment. Klepsydra, which I will present in a minute, is a combination of all this previous experience in aerospace and also as a developer of trading system, and applied to something called edge computing. So what is edge computing? Edge computing refers to these small computers installed inside different type of devices. In this case, we're talking about a satellite. The key feature of these small computers installed in these devices is they are connected to a large number of sensors and other sources of data. The newer scenarios, the newer computers tend to be connected to more and more data sources. New satellites produce volumes of data that have not been seen before, and these small computers have to process it all. This is the case of space. However, the same happens in other sectors. For example, in aerospace, helicopters, aircrafts, and drones are facing exactly the same situation. They have small computers inside connected to a growing number of data-producing elements, sensors, networks, etc. Again, the same happened to another sector, which is particularly important because it's where the number of sources of data has grown the most, which is automotive. Nowadays, a car can have up to 100 sensors or even more. Self-driving cars are facing the use of even better sensors and even more sensors, and they are very much stretching the capabilities of these small computers. And this is one of the reasons why we haven't seen self-driving cars yet in the streets. The problem of data processing is absolutely massive in this sector. In particular, edge computing, which is what I mentioned, these small computers, are facing a very important issue today, which is that while the computers are increasing as well, increasing in capability, they are obviously better computers for the edge, better and better every year, that's for sure. However, the volume of data that these computers have to process grows even faster. So we are starting to see a gap between the volume of data and the capability of the computer. Why is this important? Because this area here, this gap, corresponds to data losses. This is where the data is lost. We don't process some of the data arriving to the computer. And this produces all sorts of problems. Collisions, in the case of robotics and drones. More importantly, mission failures, in the case of space. Many past famous mission failures are because of this data processing issue. And like I said earlier, the most important of all is the self-driving cars. What is preventing the appearance of the real self-driving car in a production environment. This problem, however, is not new. It's not a problem that has been discovered now with edge computing. It has existed for a while. It appears roughly 10 years ago in this sector that I covered at the beginning, called trading. Trading is a technique used by banks to perform transactions against a stock exchange. The more transactions they perform per day, the more money they make. This is pretty much in essence, what banks are doing in terms of trading software. And like I said, 10 years ago, there was a big revolution because there was a development of certain techniques called Logfree programming. These algorithms using Logfree programming are extremely fast, can increase the performance of a computer substantially up to 4 times, or even in some cases up to 10 times. So what I have done in Klepsydra initially was to use the same techniques, but apply to edge computers. So we use exactly the same techniques as trading systems, but apply to edge computing, achieving this level of performance that you can see here. So what are these log-free programming techniques? Log-free, the technical name is this, compare and swap. Compare and swap refers to a computer instruction, an instruction in the processor that enables you to update a piece of data in parallel by multiple threads, by multiple elements are trying to update the same data at the same time, and this can be achieved by using compare and swap. Okay, this is the most important element of this. It's an atomic operation in the sense this is just one operation, not many. It's one operation. This is why the name is like this. Moreover, these techniques were invented roughly in the 70s, so 50 years ago, but they didn't really become popular until the early 90s, when these were made available to the most higher level languages like Java and C++. But the real revolution came 20 years later, like I said, when the appearance of high-frequency trading techniques in the banks. So why is this log-free particularly fast? Why these cache operations are fast? Without cache, before the existence of cache, the world of parallel processing in a computer looked like this. A lot of people cramming, trying to access resources, fighting each other, trying to access to a place or something like this. And this was extremely power consuming, non-deterministic, so that means that you don't know what is going to happen in the next millisecond of the computer. These are very heavy operations. This is why, at the moment, many of these sectors that I mentioned, including space, are not allowed to use these parallelization techniques. However, when we talk about cache, the behavior is completely different. You have to think of cache as opposed to this chaotic queue as a luggage belt, an orderly luggage belt where people can just go and collect their luggage. You cannot access the whole belt. You can access just your luggage. This is the most important thing, but you always have access to it in an orderly manner. This is a more granular way of allocating resources, more or less. This is why this is particularly fast, particularly low weight, and are becoming a very important technique in the parallelization of data processing. At Klepsydra, we have built a software for this, a solution. We call it SDK. It's basically a framework that developers can use to develop software using this. Just to show you the level of performance we have, here is a chart for a space computer. We see a similar chart to what I showed you at the beginning in the part of trading, where Klepsydra can increase, in this case, 4 times the volume of data that can be processed in these computers, just by using these techniques coming from trading. Moreover, we have applied another technique. I invite you to look into research in this field called pipelining and parallelization. I really much think that these areas are of massive growth, and for those of you that are studying ITs, it's a very important area, as well as log-free. The traditional parallelization techniques, or vectorization, as they're also known, enable you to perform large mathematical operations in a parallel manner. So, for example, if you are performing a matrix multiplication, instead of multiplying different parts all together, you multiply different parts in different threads, so in parallel. However, pipeline is a different technique in which you have a behavior similar to those in an assembly line, where each part of the assembly line performs one task. This technique is particularly well suited for these scenarios because it reduces the power consumption and increases the amount of data that can be processed. Imagine that each card in this assembly line is like an image, for example, coming from a camera, and you want to do certain things with the image, object detection, filtering, etc. So each step of the assembly line will be performing one part of this algorithm on the image. With this, we have developed yet another product combining our log-free technique and the pipelining, which is our artificial intelligence software. There is a demo in our website. If you go to the website, you will see this demo that shows the level of performance we can achieve. The demo is for an area called vision navigation. In particular, we are analyzing images from an asteroid and trying to detect how to land on it using artificial intelligence. And then we have to chart throughput, so how much data we're actually processing. Blue line is Klepsydra. As you can see, we process double than traditional techniques. And CPU usage. where Klepsydra, the blue line again, is using half of the power as one of the market leaders in the field. Why is this important? Because we can process double amount of data with half of the power, meaning that this can be placed in this small satellite that I showed at the beginning and enable it to perform navigations without any incidents, as opposed to the current situation where this is a very risky maneuver. The applications for space are not only related to vision, like I said, vision navigation, but also to Earth observation, which refers to satellites with cameras pointing to Earth and analyzing the data, but also for telecommunication satellites. This is another area where artificial intelligence is becoming very important. And this is the journey up of the Hobbit. Now, the back again part is that we are seeing that there is very good applications as well on Earth, from IoT, robotics, etc., but more importantly, what I said at the beginning about self-driving cars. Self-driving cars are really facing this massive issue of data processing with massive data losses that only a software like the one I presented, coming from the trading techniques, can really solve. So, in conclusion, what I show you here is a technique coming from a terrestrial application from investment banking. It's a software that is extremely fast. It's probably one of the fastest software techniques in the world. We have enabled this software to work well in space, in the space sector, and now we're seeing that this software can be used in other sectors as well. So there I'm back again. Okay, I invite you again to look into this research that I mentioned, pipelining and Logfree, and I thank you very much for your attention. Bye-bye.